Now coming to, that is, we have already completed hydrogen bonding. We have seen the properties of the hydrogen bond, we have seen it. We have seen the types of hydrogen bond. Just let me tell you that intramolecular hydrogen bond has properties just opposite to that of intermolecular hydrogen bonding. Alright, like intermolecular hydrogen bonding undergoes association, due to which it has got high melting point, high boiling point, high solubility. Alright, it has got high viscosity. So, but the properties of intra is different from that of inter. We have already seen it. Alright, we have also seen that ice forms a cage-like structure, due to which ice is lighter than water and it floats in water. Alright, because you know that ice is floating in water, because ice forms a cage-like structure. It forms a cage-like structure. This sort of clear. It forms a cage-like. Now, how it is so? That is, I'll show you here. How it forms a cage-like structure, I am showing you here. So, you can see it here. That is hydrogen. Here it is. This one, hydrogen. Another one is here. This one is here. And this is another water molecule. This one. And we are having here this one. So here it is. Yeah. This is water one. This is another water. 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 Okay. So in this way, you can see that ice, when water molecule, these are water molecules, see 6 water molecules, 1, 2, 3, 4, 5, 6. Now 6 water molecules are taken. When they arrange themselves in this way, it forms an ice cube. It forms. So ice generally forms a cage-like structure. You can see it. It forms a cage-like structure, due to which the inner part is hollow. You can see. As the inner part is hollow, the volume will be more. If the volume will be more, the density will be less, because density is inversely proportional to volume. Got it? Again I repeat, when ice forms a cage-like structure, that means when water freezes to form ice, it arranges itself in this manner. You know that ice is lighter than water, ice is less dense than water. Why? Because we have read in physics that due to anomalous expansion, that is when water freezes to form ice, when water is being cooled below 0 degree, when water is being cooled below 4 degrees centigrade to 0 degrees centigrade, the volume increases and density decreases. We have studied in anomalous expansion of water. You have studied it. This is called anomalous expansion. Alright, because water behaves differently compared to that of other liquid. Generally, what you find is that when liquid is being cooled, the volume decreases. But when water is being cooled, its volume increases beyond 4 degrees centigrade. Alright, but why? Why the volume increases? The reason is here. The volume is increasing because when water molecule freezes to form ice, it forms a cage-like structure, due to which the inner part is hollow. You can see it here. Alright, the volume increases, due to which when volume increases, density decreases, because density is inversely proportional to volume, and hence ice floats in water. This is the reason. We can say that. Clear? So now here we got it, this particular fact. Already we have studied some of the properties of the hydrogen bonding. Alright, we have studied it. So hydrogen bonding is very important. Hydrogen bonding is giving rigidity or flexibility to our muscles, because and the tissues which is being there, the hydrogen bond is being present in it. It gives rigidity and flexibility. Due to the presence of hydrogen bond only, water is a liquid. Otherwise, all other substances, all other hydrides in that particular group, that is group 16, H2S, H2SE, H2T, all are gaseous. Except that water is a liquid. Due to the presence of hydrogen bond only, water is a liquid. Otherwise, All other hydrides of group 16, that is I said you, H2S, H2SE, H2TH, all these are gaseous. Got it? And as water is a liquid, you know what is the uses of water. I don't have to say what is the uses of water, because as water is a liquid. So in this way, the clothes which you are wearing, the cotton clothes you can see, it is so tough. Alright, it is elastic slightly, it is tough, it is durable. That is nothing but due to the presence of hydrogen bond. We can say that. Clear? For that reason I said the muscles and the tissues, hydrogen bond is there, the ligaments, hydrogen bond is there, which gives you durability, which gives you toughness. Alright, which gives you flexibility. We can say that. So these are the uses of the hydrogen bond, and some more of it you can go through in your book. You can get it from your book. Okay, fine. Now this is all about the hydrogen bonding. So I've finished with you the hydrogen bond, so to say. In the last class only I've done it. Little more I thought that I should say you. So hence I said about the hydrogen bond. Fine. Now next we are going to come to is the van der Waals forces. Alright? Van der Waals forces. We can say that. Now, what is van der Waals forces? Now, van der Waals forces is nothing but a weak electrostatic attractive forces existing between all kinds of atoms, molecules and ions when they are brought sufficiently closer to each other. Again I repeat, it exists between all kinds of atoms, molecules and ions, all kinds of, remember it, listen carefully, it exists in all substances. Condition is that they have to be brought sufficiently closer to each other. Then only the van der Waals forces will exist, and it's a weak electrostatic forces. So 3 points you need to remember it. One is it's a weak electrostatic forces. It exists in all kinds of substances, atoms, molecules and ions. And the third is when they are brought sufficiently close to each other, then only these forces will exist. Fine. So in this way, this is called van der Waals forces. You can say that. Now, van der Waals forces is of 3 types. One is your dipole-dipole interaction. The first is what I said, dipole interactions. Dipole interactions. We can say that. Now, what I said, dipole interactions. Now, this is also called as, other name for it is also known as Kissam forces. It is also said to be as Kissam forces. Dipole interactions. Means, for example, let us take that is an HCl molecule. HCl. So, you know, H is positive and Cl is negative. You know that because Cl is more electronegative than hydrogen. Okay. We are having another HCl molecule. Okay. Another HCl molecule. This sort of. Again, H positive and Cl negative. It arranges itself. You know it. You have read it in BSc Pure theory. So, in this way, what is the forces when they come closer to each other? What is the forces exist between two HCl molecules which holds them together? Dipole interactions. That is the Kissam forces. What I said, dipole interaction. Di means 2 poles. Here also 2 poles. You can see. Alright. So in this way we can have another HCl molecule, another HCl molecule, another HCl molecule. Similarly we can have HF molecule. Similarly we can have water molecule. Similarly we can have ammonia molecule. Alright. So when 2 water molecules they come closer to each other, what happens? What is the force which exists between them? That is dipole interactions. Apart from that also, what you can say is that hydrogen bonding is also there, we can say. Alright, but hydrogen bonding is much more stronger than dipole interactions. Remember it, it's a weak force, it's a weak bond, we can say that. Clear? Fine. Now in this way, when the dipole interaction is being taking place between 2 polar molecules, these 2 are polar molecules, we can say that. So hence dipole interaction takes place between which kind of molecules? 2 polar molecules. Like HCl and water, that is also 2 polar molecules. Like HF and ammonia, that is also 2 polar molecules. HF and water, that also is 2 polar molecules. So when the 2 polar molecules, listen carefully, when they are brought sufficiently closer to each other, then the force which exists between them, which holds the 2 molecules closer, which holds the 2 molecules together, is known as your dipole interactions or Kissam forces. I hope you got it. Now next, the second force is your dipole induced dipole interactions. The second forces. What I said? Dipole induced dipole interactions. Now this force is also said to be as nothing but Debye forces. This is said to be as Debye forces. Debye. You will be reading it later on. The Debye is a unit of dipole moment. It's a unit of dipole moment. Now, just now we studied about which kind of molecule? We studied about two polar molecules. Fine. Now, when one molecule will be polar and another is non-polar, the next is, we studied about two polar molecules. Now we will take one polar and another non-polar molecules. Then what the kind of force exists between them? This is that particular one. Dipole induced dipole interaction. What does it mean? That means when a polar molecule is brought near a non-polar molecule, then due to induction, alright, the non-polar molecules also get slightly polarized. Due to induction. Listen carefully. For example, let us say a polar molecule is a water molecule and a non-polar molecule is a methane molecule. Alright. Methane, you know, is slightly soluble in water. Slightly, very slightly. It is soluble in organic solvent. Alright. Or let us say an ethene molecule, alkene molecule. Alright, so in this way, they are the non-polar molecule. Methane, propane, ethene, ethyne, they are the non-polar molecules, so know it, organic substances. So when this molecule is being brought near a water molecule, water is a polar molecule. So slightly you find that these substances are soluble in water, slightly. Methane, ethene, all these are gaseous, they are slightly soluble in water. I said slightly, listen carefully. I did not say they are highly soluble in water, they are highly soluble in organic solvents. They are slightly soluble in water. Why? Because when water molecules is brought near to the ethene molecule or a propane molecule or a methane molecule, alright, that is a non-polar molecule, then it gets polarized, alright, which is known as dipole induced dipole interaction. So I will explain you here. Let us say this is a polar molecule, this one, a non-polar molecule. This is a non-polar molecule in which the charges are equally distributed. Alright, in case of non-polar molecules, you know the charges are equally distributed. Just now I will tell you after some time about the polar and non-polar. Of course, you have studied in the lower classes also. The charges are equally distributed in case of non-polar molecule. And let us say this is a methane molecule. Let us say methane. This is CH4. A molecule is CH4. Or you can take any other non-polar molecule. Understood? It should be non-polar. Understood? Remember it. And here I will be taking a water molecule. We can say that water molecule. I will be taking it. Clear? So water, it is nothing but HOH, H plus and OH minus. It is del plus and del minus. We can say that. So it is a polar molecule. Now when this methane molecules comes very close to that of polar molecule, remember it should be very close to each other. I have already studied the condition. Now this is your water molecule, which is a polar molecule. When it comes very close to each other, then what happens is this methane molecule gets slightly polarized. See, it gets slightly polarized due to induction. When it comes very close, I don't say they are in contact with one another. If you can't see, I'll just decrease this distance a little bit. Now you can see. When it is brought very close to each other, due to induction, this non-polar molecules also get slightly polarized. It develops del minus and this is del plus. It gets slightly polarized. So what is this? Forces which exist between this polar and the non-polar molecule is known as what? Debye forces. It's said to be as Debye forces. Alright? Due to this reason only, some non-polar molecules are slightly soluble in polar solvent. As I gave you the example, like methane, ethene, propane, butane, butene, alright, ethyne, they are slightly soluble in water. The reason is that due to the existing of Debye forces when they are brought closer to each other. We can say that. Clear? So along with that I am telling the uses also, you can say that. Clear? Fine. Now next is, so dipole induced dipole interactions, you understood the Debye forces which exist between polar and non-polar molecules. Fine. Now polar molecules, the Kisam forces, the what you can say, the applications, let me tell you, is that when the two polar molecules they are brought closer to each other, then Kisam forces exist, due to which the polar molecules gets liquefied under low temperature and high pressure. This is the condition for liquefaction, low temperature and high pressure. They gets liquefied easily, because when they are brought closer to each other, they come closer also, still closer, because they are having a force, Kisam forces, which is called dipole-dipole interactions, which brings them still closer to each other. And due to this reason, what happens is that the gaseous molecules, it turns into a liquid state, but the condition should be low temperature and high pressure. They come closer and then they get liquefied. That's an application of what you can say Kisam forces, we can say that. Now the third one is your, that is temporary temporary dipole induced dipole interactions. Temporary dipole induced dipole interactions, we can say that. Clear? So what is the example we can give it upon it? We can give the another name for it. It is nothing but is your London forces or dispersive forces. Dispersive, D-I-S-P-E-R-S-I-V-E, dispersive forces. London forces or dispersive forces. What I said, temporary dipole induced dipole interaction. See, I have used the word temporary. Temporary means this exists in which kind of molecule? This exists in between two non-polar molecules, because we have finished polar Kisam forces. We have finished polar non-polar Debye forces. Now we are going to do two non-polar molecules. Alright, two non-polar molecules. Fine. Suppose we are having that is methane molecule and an ethane molecule, let us say. Alright, methane and ethane molecules. So definitely they have got two difference in the sizes. You know that. That is, let us say this is a methane molecule, which is generally it will be smaller because methane is CH4, a smaller one, and ethane will be slightly bigger. Alright, this is an ethane molecule C2H6, which is nonpolar, and this is methane molecule, which is also nonpolar. So there is no question of polarity here. Fine. So when this smaller molecules is going to hover around the larger one, alright, hover means it is going to move around the larger one. A certain point will come. Listen carefully, when this particular what you can say non-polar molecule, that is the electrons which is present in the outermost shell, it is going to pull momentarily, temporarily the methane molecules towards itself. Alright, again I repeat, when the methane molecule is hovering around this ethane molecule, when the smaller one is going to hover around the larger molecule. Now as it is a larger molecule, so the electrons which are present in the outermost shell, they are free electrons, you know that. Alright, larger means definitely it is large distance from that of the nucleus. Now if you don't understand, you will say, sir, here ethane is a compound, where it is, okay, we can take two different elements, we can take it and we can explain it. Alright, for example, we can take here what you can say, that is nothing but we can take here oxygen molecule, which is smaller one, and here let us take a nitrogen molecule, which is slightly bigger. Alright, clear? We can take this. That also we can do it. Or we can take a fluorine molecule, which is still smaller. We know that fluorine, because when you move from left to right across the period, atomic size decreases. So this is a fluorine molecule, smaller, and this is a nitrogen molecule, which is quite bigger compared to that of the fluorine, we can say that. So that also can be taken. If you don't want methane, you can take this also. Now you can understand it, that electrons which is present in the outermost shell in case of the nitrogen molecule, alright, it is going to pull momentarily the fluorine molecules towards itself. When the fluorine is going to hover around the nitrogen molecule, momentarily, temporarily, it is going to pull towards itself. Due to this particular pull, what will happen is that a force will be created between them. Temporarily, a force is being created between them, which is known as London forces or dispersive forces. We can say temporarily it is being created. Repeatedly I am using this word, temporarily, when this smaller molecule will be hovering around the larger molecule, but both should be non-polar in nature. Any molecule you can take, both should be non-polar in nature. Then temporarily a point will come when the electrons in the outermost shell is going to pull the electrons towards itself, and hence momentarily a force will be created between them. That is called London forces. Now what is the application of this? The application is that is when you are liquefying these gases, you know that these gases are not easy to liquefy. You read in lower classes somewhere, you read it. These gases are not easy to liquefy. The reason is this, because they are non-polar in nature. So if you provide a low temperature and high pressure, what you find is that some of the gases get liquefied. Again what you do is that you repeat the process. If you have read the process of liquefaction, if you remember the process of liquefaction which is studied in the lower classes, alright, a cycle is being set up. The gases which gets liquefied, it is being collected below, and the one which is not liquefied, again it goes to the compressor, again it goes to the heat exchanger where the temperature is being brought down, again it goes to the cooling tower where it passes through the spiral pipe, and the temperature is being lowered and pressure is increased and the gases gets liquefied. So till all the molecules get liquefied, the chain is repeated, the cycle is repeated. Why it is repeated so many times? The reason is this, Because when momentarily it comes, the non-polar molecules get liquefied. So slightly small, some molecules get liquefied. The one which does not liquefy, again the process is repeated. Again the process is repeated. In this way the process gets repeated one after another until all the gases gets liquefied. Alright. So this is the applications of the London forces. Still more applications are there, as I said you. This is one of the applications, the major applications of the London forces I have explained to you. Fine. So in this way we have got three types of van der Waals forces: Kissam forces, Debye forces and London forces. Now remember it, that is on the basis of this van der Waals forces only we can say another applications, I remember it. So we can explain why fluorine is what you can say gas, chlorine is also gas, bromine is a liquid and iodine is a solid. Because when you come down the group, listen carefully, atomic size increases. Now this is fluorine, chlorine is little bit bigger, bromine is quite bigger and iodine is still much bigger, we can say that. So when you are coming down the group, the atomic size increases, due to which van der Waals force increases. Because remember it, more is the molecular size, more is the van der Waals force. Listen carefully, as the molecular size increases, van der Waals force increases. Van der Waals force directly depends upon the molecular size, we can say that. Like ethane and butane if you take, which is having higher van der Waals forces? Butane molecules is having higher van der Waals forces. More is the molecular size, more is the van der Waals force. So as the van der Waals force is increasing, so for that reason what you find is that it changes from gaseous state to solid state. Because here the van der Waals force is less, so it is gaseous. Here it is more, the molecules come closer, it changes from gaseous state to liquid state. Here it is still more, the van der Waals forces, the molecule comes still closer and changes to solid state. So in case of halogens, that is the first two elements are gaseous, then after that is liquid, after that is solid. The reason is explained on the basis of van der Waals forces only, we can say that. We can also explain that graphite is soft because between the two layers of graphite we are having the van der Waals forces. And iodine is hard because iodine is not separated in layers, we don't have the layers. Iodine I am saying, yeah, of course iodine is also hard. At the same time I should say diamond. Graphite means I should compare diamond. Alright, so diamond is hard. The reason is that in case of diamond, strong covalent bond is being present. Strong covalent bond is being present in case of diamond, due to which diamond is very hard. But in case of graphite, we are having the hexagonal layers. One hexagonal layer is joined to another hexagonal layer by van der Waals forces. So in this way we can say that. Alright, that is we can explain the liquefaction of noble gases on the basis of van der Waals forces. Noble gases, you know, it does not liquefy easily. They do not come closer to each other, do not form molecule. But we can do it under low temperature and high pressure, because when they come closer, there exists a van der Waals forces. Alright, otherwise why they will liquefy? They do not have a tendency to get liquefied. Why? Because they are non-polar in nature. Their outermost shell is fully filled. So why they will form a molecule? Any, they will not form a molecule, it will not form any two. Then how does they get liquefied? That is I say, when they are brought closer, two neon atoms, when they are brought closer, what happens? A van der Waals forces results between them. Alright, which I explained you just now, London forces. And hence, what you find is that when they are brought closer to each other, they get liquefied under low temperature and high pressure. So the liquefaction of the noble gases can also be explained on the basis of van der Waals forces. Because in noble gases, no other forces exist. Because we don't have a covalent bond, because noble gases like neon, argon, krypton, xenon, helium, they do not form molecules, so hence they do not have a covalent bond. Then why they will liquefy? The reason is that because when they are brought closer to each other, correct, the van der Waals forces exist and hence it changes from gaseous state to liquid state. Clear? So all this is about your van der Waals forces. Thank you.